Good morning, everyone. In this talk, I'm going to introduce my recent research project, MATCH, an MPI fault tolerance benchmark suite. This is a collaborative work between the University of California, Merced and the Lawrence Livermore National Laboratory. This work was performed when I was an NSF Trusted CI Fellow. As we know that MPI has been extensively used in HPC systems, and as reported, future HPC systems are expected to incur a much higher process and node failures. For example, the Sequoia supercomputer located in Livermore National Lab reported a mean time between node failures to be 19.2 hours in 2013. Most recently, the Taurus system located in TU Gerasen reported a mean time between node failures to be 3.65 hours. These crucial facts lead to an increasing concern about fault tolerance designs to MPI failures in HPC code. However, there is no structural way to compare different MPI fault tolerance designs in existing work. We design and develop a benchmark suite called MATCH to study the performance efficiency of different MPI fault tolerance designs and to guide the selection and development of efficient MPI fault tolerance designs in different scenarios. We consider MPI fail-stop failures, or called MPI process and node failures in this work. MPI process and node failures occur in production HPC systems due to power outage or other issues. When this type of failure occurs, application execution has to stop if the communication is not fixed. MPI failure recovery has 6 recovery modes. First, global. In this case, the application execution rolls back to a global state to fix a failure. Second, local. Here, the failure can be repaired locally without starting over the execution. And backward. Here, the application execution must go back to a previous state in order to survive a failure. And forward. In this case, the application manages to bring all failed processors back in order to resume the execution. And then shrinking. Here, the application execution can continue with the remaining survival processors. And in HPC system, the global backward non-shrinking recovery naturally fits into the bulk synchronous parallel paradigm of HPC applications. Here, bulk synchronous parallelism means that different processors perform the same computation concurrently on different parts, but the same amount of data. After each computation step, all processors conclude with a barrier for synchronization. As a result, we focus on global backward non-shrinking recovery in this work. We use the fault tolerance interface FTI for data recovery or checkpointing. The fault tolerance interface is easy to use. It only requires users to tell the memory address, data size of the data objects to be protected. And we use ULFM, user-level fault mitigation library for MPI recovery. ULFM is a leading MPI failure recovery framework, which provides shrinking recovery and non-shrinking recovery. And in this work, we focus on non-shrinking global backward recovery. ULFM handles failure recovery in an error handler, and in which there are three essential phases. First, it creates a new communicator where the data processors in this communicator were removed. And then it creates a newly spawned communicator where the data processors are recreated. And lastly, it creates a new communicator which merges the shrunk communicator and the newly spawned communicator. And here we also use Reinit++ as an alternatively recovery framework besides ULFM. Reinit is particularly designed for global backward non-shrinking recovery. And you can find the details of Reinit++ design from the paper published in IST20 this year. And the good points of Reinit++ is that it only provides one interface for MPI failure recovery, called MPI Reinit. And the entire recovery process is transparently implemented in the MPI runtime, which is transparent from users. And here, the third parameter of MPI Reinit is a pointer to the function to be protected. And Reinit++ also defined three MPI states for new, reinit, and respawned processors. And here we provide two use cases of ULFM recovery and Reinit++ recovery. The Reinit++ recovery has much less programming effort than ULFM recovery. In the Reinit++ use case, we simply move the content in the original main function into resilient main, and then add MPI Reinit pointing to the resilient main function. However, the ULFM recovery requires users to define an error handler, to add the error handler to the MPI word communicator, and to set up a rollback point for survival processors. And more importantly, ULFM requests to define the MPI word communicator as a global variable to enforce the repelled communicator to take effect immediately. However, Reinit++ transparently implements failure detection and MPI recovery into MPI runtime. And ULFM asks users to handle failure detection, MPI recovery all by themselves. And ULFM made significant changes to the source code. A well-known challenge for application-level checkpointing is that it requests users to provide data objects for checkpointing. It is difficult for users who are not domain scientists of the application. And to solve the problem, we developed 3 principles to find necessary data objects for checkpointing through data dependency analysis. The 3 principles are: first, the data objects for checkpointing must be defined before the main computation loop. Second, the data objects for checkpointing must be used, write, or read within the main computation loop. And third, the value of the data objects for checkpointing must vary across iterations of the main computation loop. And based on the 3 principles, we design an algorithm for finding data objects for checkpointing. The input to the algorithm is the set of locations used in the main computation loop, and the set of locations defined or allocated before the main computation loop. In the first step, we check the values of locations in the set of locations used in the main computation loop. In order to remove those locations that do not change its value across iterations. And then, in the second step, we remove any repetition from the 2 sets of locations. And finally, we look for a match between the 2 sets of locations, and we tweak those matched locations for checkpointing. And here we find 6 proxy applications getting from leading benchmark suite as workloads for match. So those workloads are getting from the ECP proxy application suite and Lawrence Livermore National Lab ASC proxy applications suite. And the 6 applications represent the most important HPC application domains in scientific computing, such as iterative solvers, multigrid, and molecular dynamics. And for experimentation setup, we construct 3 fault-tolerance designs using Restart, ULFM, Reinit++, and the fault-tolerance interface, FTI. And we use a fault injection code to emulate MPI process at node failures by raising a termination signal on a child process for emulating process failure, or by raising the termination signal on a daemon process for emulating node failures. And these slides presents the results for different scaling sizes with a process failure. Here, we use HPC-CG as a representative of the results. The results for other benchmarks are similar. Note that we did not show the time for reading checkpoints here because the time for reading checkpoints is in the order of milliseconds, and reading checkpoints only happens once. And the results are shown in this figure. The x-axis is the number of processors, and the y-axis is the execution time, which we break down into the time for failure recovery and the time for writing checkpoints and the pure application execution time. By observation, overall, we can see that Reinit++ recovery is much faster than ULFM recovery and restart recovery. And Reinit++ recovery scales very well as scaling up. Also, we can see that ULFM recovery overhead gradually increases as scaling up. And we observe that ULFM slightly delays the application execution and the time for writing checkpoints. And to find the reason, after closely examining the ULFM implementation, we find ULFM uses heartbeat operations to actively detect any failures. The heartbeat operations constantly occur and affect the application execution and checkpointing. Also, ULFM uses many collective operations for both failure detection and recovery, which over-occupies the computational resources and significantly delays the communication and computation. To conclude my talk, we present detailed instruction to implementation of ULFM, Reinit, and FTI to MPI applications. And the code is available at the following GitHub link. And also, we propose a data dependency analysis tool to detect data objects for checkpointing. This is essentially useful for applications with many data objects to be checkpointed, whereas the programmer does not understand the application well. Mesh also provides a foundation to future HPC fault tolerance designs, in which programmers can develop new MPI fault tolerance designs on top of Mesh. And finally, this presentation was performed under the auspices of the Department of Energy by Lawrence Livermore National Lab. Thank you very much for your attention, and I'm happy to take any questions.